In this video, I'll be showing you guys how to combine series and parallel resistors together to get some equivalent resistance. Now, what you're seeing here is basically just something you call a terminal. And anything past this point of the circuit, you don't really care on what's the other side of it. All right, it could be 3 voltage sources, it could be 10 capacitors or something. Doesn't matter. We only care about combining all these resistors. And the reason why you want to do this is because sometimes when you do this, only sometimes, of course, but sometimes when you do it, it makes solving the circuit easier. So, of course, you want to know how to combine parallel series resistors so you can get some final equivalent resistance to make equations simpler, right? One resistor is easier to calculate than 4. So, if you don't know how to calculate, how to add together series and parallel resistors separately, first you need to know that. So I'll leave some video links down in the description for both of the videos that I made on that if you still need work on that. But let's go ahead and start with this problem. We notice that these two resistors are in parallel, right? They're in parallel, not geometrically, they are in parallel within the circuit. Okay, so they share the same 2 nodes. So what we have here is 2 parallel resistors. How do we add them together? We can use this formula to find the equivalent resistance. The resistance of resistor 1, the resistance of resistor 2, over the resistances added together is equal to the equivalent resistance. So if we do 4 times 6, 4 times 4, no. 4 times 6 over 4 plus 6 is equal to 24 over 10, which is equal to 12 over 5 ohms. So what we actually do here, let's box it up in green, and we can redraw this circuit with the resistors combined together, with the parallel resistors combined together. So what we redraw here is the new 12 over 5 ohms resistor for the equivalent resistance of this parallel part of the circuit. And of course the resistances of the previous resistors are the same. The resistors where you did nothing with them. Alright, well now the resistors are in series. And you don't even need to know too much about series circuits. You literally just need to know resistors in series. They're end to end. Okay, you can add them all together. So if we add all the resistances up together, we have 11 plus 3 plus 12 over 5 ohms. And this is equal to 82 over 5 ohms. Put this in blue to differentiate it. So, well, we have the total equivalent resistance. So right here, we just need to draw one singular resistor. And this new resistance is 82 over 5 ohms for the final equivalent resistance. Now, I really like this example here because it shows you what parallel resistors actually are in a circuit. So, we can tell that these 2 resistors are parallel geometrically, right, off the drawing. But here's the thing, they do not share the same nodes. Keep that in mind. So, these parallel resistors do not share the same nodes. There's a node here, there's a node here, and this entire bottom portion is also a node. So, look at this. These 2 resistors do not share the same node end to end, right? This end connects to this node, this end connects to this node, but, well, both of the bottom portions of these resistors also connect to the bottom node, the total bottom node here. So since they both don't share the same node, technically they aren't in parallel. Although they are parallel geometrically in the circuit, they aren't parallel circuit-wise. So what can we do for this? Well, technically, although these 2 aren't parallel, these 2 are in series, right? They are connected end to end. So what you can do is actually add these 2 resistances together, 6 plus 6. I don't need to write that down, hopefully. And we can redraw the circuit to look like this. And this new resistor here, this is 4 ohms, this is 6 ohms. This new resistor was the 2 resistors added together previously. So 6 plus 6 is, well, 12 ohms. Now, the choice doesn't matter. I could have put the resistor up here as well, or I could put it even in the bottom, right? It doesn't matter. They still share the same node at the end of the day. If I put the resistor up here, this would be a node that they connect at, and this would be a node that they connect at, right? This entire resistor stretches down and then touches this portion of the node. So the ends of both the resistors are connected to this node, and the fronts of both the resistors are connected to this node. Doesn't really matter where I draw it. And that's the same, actually, if the resistor was down here, right? It'd stretch all the way up, and one portion would hit there. Basically, the ends of the two resistors would hit this node, and the fronts of the resistors would hit this node. Now, I'm saying end and front very lightly there. I'm just saying end and front differentiate the sides of the resistors. There's no actual name for the end and the front of the resistor. So, now that we have two resistors that are in parallel, we have 6 and 12. Well, we can use our formula for parallel resistors, only two parallel resistors. So 6 times 12 over 6 plus 12. And this right here is equal to 72 over 18. Which, if you simplify this, it's simply equal to 4. So the new resistance of these two parallel resistors added together is 4. Let's go ahead and draw the new circuit. Remember, we didn't do anything with this resistor yet, this guy right here. But we combine the two parallel resistors so that they just look like this, right? These two just connected together. So our new resistance is, let's write it with yellow like I have been, 4 ohms. And our resistor we did nothing with is 4 ohms. Well, we have a series here. That's pretty clear. So if we just add these two together, we get the equivalent resistance, 4 plus 4 is equal to 8 ohms. I may have jumped the gun a little bit. Yeah, this is an atrocity of a circuit. But when I was doing circuit analysis, this is something that I had to deal with. All right, so you guys have to deal with it too. And if you can solve this, honestly, you can connect any resistor you want. You're a professional now. All right, you're computer engineering. Jitty said so. But let's go ahead and start this. What is the first thing that I noticed? Well, the first thing I noticed is that these two resistors are in series. Okay, well, they're in series, right? Let's, of course, copy and paste this. If they're in series, we could simply add the two resistances. Let's go ahead and write a new resistor, 10 plus 2, which is equal to 12 ohms. Actually, let's use a different color for something that we modified. So 12 ohms is the new resistor. Resistance of the combined series resistors. Well, another thing is that the ends of both of the resistors share the same node. Okay, another thing that we can write down. Let's go ahead and copy this one. So since they share the same nodes, we could simply use parallel resistors function. So R1 times R2 over blah, blah, blah. You get it, okay? I wrote it down in the first problem. So 12 times 6 over 6 plus 12. And we solved this in the previous problem. It was simply equal to 4 ohms. So if we combine these two resistors right here, oh, good Lord. Maybe I should pause the video during these times. But if we combine these two resistors here, you get a new resistor that is 4 ohms. Of course, green for the ones that are modified. Let's fix this up a little bit. Well, here's the thing about my choice of drawing. Again, I just drew it in this location because it'd be easier. I could have drawn the 4 ohms diagonally. Like I could have just completely omitted this corner, and then now the circuit would look weird, but I could have drawn the 4 ohms like this. Right? It doesn't matter. My choice of drawing does not affect how the circuit works. All right. Well, now that we have this, what is up next? Take a guess. You guys take a guess. You took a guess? Yep. The guess is that these resistors are in series. So this 4 ohm and this 8 ohm resistor are in series. So we can combine these two together. So 4 plus 8, yikes, that does not look good. 4 plus 8 is equal to 12 ohms. So we have a new 12 ohm resistor here. Okay. What is next? Well, I'm going to have to erase some previous ones. I'll keep the original problem, actually, and erase the other steps. So just go back into the video if you want to look at the previous steps. Okay, I can't click that. But, again, we have parallel resistors, right? They share the same node. Technically, the node is this entire top portion and bottom portion. So since these two share the same node, 6 and 12, we've already discussed this. There's a 6 and 12 parallel resistor. We've solved for it before. It simply becomes 4 ohms. So we can actually kind of just erase this and combine the two parallel resistors like so. So this right here, let's draw the corner. Let's fix the corner. And this right here is the combined parallel resistor. This guy's the combined parallel resistor at 4 ohms. All right, we're taking a step forward. Well, again, we have resistors in series right here. 2 in series. So You can add them together. I think you guys get the point of this at this point. It's just a bunch of resistors in series, parallel, series, and parallel, back and forth, back and forth. But 4 plus 4, series and together, you get 8 ohms. Okay. Again. We have a parallel resistor here. These two are parallel since they share the same node. And let's mark out the nodes for you. So this is a node. This is kind of a intersection point between elements, and this bottom portion is also a node. This bottom portion, entire bottom section that I circled, could also be considered a node, but I just drew the dot there. These resistors share 2 of the same nodes. So you could add the 2 resistances together. So if we have 8 and 8 together, what do you get? So let's go ahead and calculate that. So 8 and 8 are the 2 parallel resistors in this case. Let's go ahead and add color, different color. 8 times 8 over 8 plus 8. 64 over 16 is equal to 4. So the new parallel resistance is 4 ohms. All right, again, erase everything. Tedious process. I'm working through everything, but I think most of you probably skipped through this past this part of the video by now because it's just pattern recognition. I mean, like you see so many of this, your pattern recognition is going to kick in and be like, oh, parallel series, parallel series. Like a lot of you probably aren't even here right now listening to me say this, but again, we have 2 series resistors, 4 and 4, right? They're connected end to end. They kind of share the same path of current marked in orange. So 4 plus 4 is equal to, let's rewrite the circuit. 4 plus 4 is equal to 8 ohms. So 8 ohms is drawn here. Well, 8 and 8 are parallel, but we already calculated for 8 and 8. So the previously calculated 8 and 8 ohm parallel resistor was equal to 4 ohms. All right, final stretch. Final stretch. 2 resistors, both connected end to end. Hopefully you guys know what I'm getting at here. They're in series. So if I were to draw the last one, the last resistor, it would be 6 plus 4, which is equal to the big ol' 10 ohms. Well, what you did here was like magic. Basically, you simplified this entire thing. Oops. Oh, wrong tool. You simplified this entire thing to get a simple 10 ohm resistor, right? Isn't that way easier to do calculations with? I mean, like, who is going to want to do KCL here, and then KCL here, and then KCL here, and KCL here, and then KVL around this loop, right? And then KVL around this loop. Man, no one wants to do that. Literally just have some simple 10 ohm resistor, and makes a lot of the math a lot easier. In some cases, of course. You don't want to do this all the time. You don't want to simplify it all the time. Sometimes you want the information that you get out of this.